All right, thank you very much. And thanks for this wonderful workshop and the organizers for inviting me. It's been really great so far. I've learned a lot and good discussion. So yeah, as you said, I'm going to be talking about my work on the Newman-Penrose map and how it sort of fits in with the classical double copy. And this is work based on a couple papers from the last couple years, along with one that's hopefully coming out soon. This is a pretty optimistic archive number. But at least within the next couple of months, I think we should have a new paper on sort of extending what we did before. And this is work I've done with my collaborators, Gilly Elor, who's at Mainz, Michael Grasser, who's at Los Alamos, and Gabe Herzeg, who's at Brown. Okay. So just a little motivational slide. I don't think anyone here needs to be motivated to understand the double copy more, but the double copy in general is this idea that gravitational theories can be treated as two copies of a gauge theory. And it's been really nice on the amplitude side. It simplifies calculations, but it's only really been proven at tree level or in some specific limits. So the idea beyond the classical double copy is sort of understanding how general this relationship is and if it can be applied to exact solutions. So classical double copy is trying to map classical exact gravitational solutions to classical exact gauge solutions, and sort of starting with the most basic thing, which is the linearized solutions. So in gauge theory, that means Maxwell solutions. And on the gravitational side, that means KERR-SCHILD solutions, which I'll talk about what that means next. Also, feel free to interrupt me with questions because I always go way too fast in my talk. So any questions I would appreciate to slow me down. Okay. So the KERR-SCHILD double copy, KERR-SCHILD spacetimes are ones that can be separated in this way, where you have your full metric g mu nu, and it's equal to a flat metric plus an exact perturbation. There's a more general version also for a curved background metric, but I'll just start with the basic with a flat background. And the graviton sort of field can be factorized in this way, phi k nu k nu. So this is really nice that the spacetime separates in this way. We have a clear definition of what the graviton is in this case. So if you impose some conditions on this k mu vector, in particular that it's null with respect to both the background, the flat background, and the full metric, and that it's geodesic with respect to both metrics, then you get that the Ricci tensor with mixed indices actually linearizes in the graviton. So this is what I mean by a linear solution on the gravitational side, if I impose the equations of motion. Okay, so the KERR-SCHILD double copy looks at these spacetimes. This is sort of the OG double copy. And in that case, they look at stationary space-time, so setting the time derivatives of everything equal to 0. And they also normalize this k vector so that the time component is 1, and that's just without loss of generality. And when you do that, the Ricci tensor with mixed indices simplifies into sort of these two parts. There's the Ri0 component and the R00 component. And maybe these look a little bit familiar. So if you start with your graviton solution and you have some vacuum equation of motion, so R mu nu equals 0, you can do some abelianized version of color kinematics, replacing your kinematic vector with a color factor to define a gauge field. So phi k mu, and then if you look at this Ri0 component of your Ricci tensor, that really just looks like Maxwell's equations for the field phi k. So we get automatically that this gauge field satisfies the Maxwell equations, and then you can go even further to get the 0th copy by replacing your last k mu vector with another color factor, and you get a bi-adjoint scalar, and this R00 component of your Ricci tensor, imposing the vacuum equations of motion on the gravity side, gives you box phi 0, which is the linearized equation of motion for the bi-adjoint scalar. So this is a nice little story. You can do this color kinematics thing on the classical side, and you get sort of a similar story to the usual amplitudes. But the color factors here are trivial, so I'm going to drop them from now on. Okay. So just as an example of a space-time that you can do this for is Schwarzschild. So the simplest kind of thing you can look at. This is our metric with a flat background and phi k mu k nu. phi is 2gm over r, and the vector is just dt plus dr. So it's pretty simple. And you can look at phi k mu, which is just this, and you do some sort of replacement of your constants. So you replace your mass by your charge, your gravitational constant with sort of an electromagnetic constant, and you get exactly the field of a point charge plus a pure gauge term, dr over r here. So it's nice. We get some sort of map between intuitively similar solutions. So there's a point map, Schwarzschild black hole on the gravitational side, and we get a point charge on the gauge side. So things make sense. And people have looked at a lot of different solutions and mapped them using this Kerr-SCHILD double copy. So Schwarzschild maps to a point charge, a Kerr black hole maps to a rotating disk of charge. You can look at plane waves on both sides and they map to each other. KERR-TAUB-NUT, which is having an extra nut charge in your theory, so you have a mass and a nut charge, and Kerr, so it's rotating. That maps to a rotating dion, so you have electromagnetic charges over there. The photon rocket, which is a particle traveling along an arbitrary time-like world line, so it has in particular arbitrary acceleration. I'll talk about this in a little bit more detail, but that maps over on the gauge theory side to a linear Weikart potential, which is the potential of a arbitrarily accelerating point charge on the gauge theory side. People have also looked at these things in sort of curve backgrounds, ADS backgrounds, or DS backgrounds, and you get exactly sort of what you expect. If you have a point charge in ADS, that maps to, a Schwarzschild black hole in ADS, it maps to a point charge in ADS. So it makes sense. And then one last example I wanted to mention that I think is really interesting is the BTZ black hole in 3 dimensions, maps to a constant charge density on the gauge theory side. And this is interesting because the amplitude story, right, gravitons in 3 dimensions don't have any dynamical degrees of freedom. So this is a case where the classical double copy has a map from solutions to solutions where the amplitude double copy does not. So there's a lot of nice examples for the Kerr-SCHILD double copy. It seems to work, it seems to be intuitive, but this is only really guaranteed to solve the vacuum Maxwell equations on the gauge theory side if the original space-time is vacuum and stationary. Some of these examples, for example, the photon rocket is not vacuum or stationary, so you can apply it, but things have to be massaged a little bit to get exactly what we want on the gauge theory side. Okay. So another related version of the double copy that's going to be relevant for the Newman-Penrose map that I'll talk about is the self-dual double copy. So in this case, this was sort of motivated by trying to look at the momentum space version of the double copy. So instead of looking at position space, you have a differential operator, k mu, well, in position space, but you treat k mu as a differential operator. So your graviton is k mu acting on a scalar phi. And you can impose some null and geodesic type constraints on this differential operator so that your equations of motion linearize again, and then do the same kind of double copy procedure. So in this case, sorry, these phi's should be the same. I did far phi and normal phi, but that's wrong. They should all be the same. But imposing the vacuum equations of motion gives you just a differential equation on phi. And this turns out to be, as we've seen in a couple other talks, the Plebanski equation for self-dual gravity. And I'm being very vague about what I mean for self-dual here, plus and minus, and I'm in Lorentzian signature. So just the curvature is related to the dual of the curvature. That's what I mean. So looking at the gauge theory version of this, doing this map, we can treat our sort of gauge theory, our gauge field as k mu hat acting on phi. And if we also impose that we want the graviton to factorize into like k mu, k nu, like it did before in the Kerr-SCHILD double copy, this differential equation for phi, actually each individual part of it has to vanish. So in particular, we get that box phi has to be 0. And that is the sort of linearized version of self-dual Yang-Mills, which we have seen before. So I just want to point out the thing that's going to be relevant for the Newman-Penrose map is that whenever we have a complex scalar like phi, where it satisfies box phi equals 0, we can use this differential operator k hat to give us a solution to the vacuum self-dual Maxwell equations. So that's going to be relevant. Any questions so far? I know I'm going fast. I'm sorry. Okay. So now to the Newman-Penrose map. So we use for the Newman-Penrose formalism, which is just a way of writing down different spacetimes using a null rather than an orthonormal tetrad. So in this case, we have 4 vectors. This is only really for 4-dimensional spacetimes. So we have 4 null vectors that are sort of our basis for our spacetime. L and N are real, and M and M bar are complex conjugates of each other. And our metric can be just written in this nice simple form. This is a really useful formalism to use when you're talking about spacetimes with null directions, principal null directions, because you can align these null tetrad vectors along your principal null direction. So it simplifies a lot of things. And it's also because it's in terms of null vectors, we can easily write it like Sylvia was talking about using spinor formalism. So that'll give us some connections to twistor space that I'll talk about. But again, it's only in 4 dimensions. Okay, so we can apply this to KERR-SCHILD spacetimes. So the KERR-SCHILD metric now looks like this. VLL, I'm using slightly different normalizations for everything. So that's why it's VLL instead of phi KK. But it's V times LL is equal to phi times KK, the whole thing. Things are just normalized a little bit differently because I'm talking about a different basis. So in this case, the null, I have to make the assumptions again that L is null and geodesic, just like before. I'm also going to assume that it is shear free. So in the original KERR-SCHILD double copy, since we were only looking at vacuum solutions, shear free was implied from having the vacuum equation of motion. But here we're going to be interested in studying things that are not vacuum. So we impose this shear free condition explicitly. And then we also assume that this geodesic congruence is expanding. So the nice thing about this assumption is that it's going to fix the form of the metric up to 2 functions. So that's why we do it. But this last assumption rules out, or it excludes Petrov type N solution. So that's PP waves, plane waves. So that's a little unfortunate that we can't apply our formalism to those cases. But it does include every other example that we've talked about so far. So SCHWARZSCHILD, KERR-TAUB-NUT, the photon rocket, a lot of different things. So that's the price we have to pay. Okay, so now looking at the null tetrad for KERR-SCHILD spacetimes. So I'm looking now at these light cone coordinates over here and writing everything in terms of those because I'm dealing with null things. And my tetrad looks like this, NL, M, and M bar, in terms of only 2 functions that show up. So that's the nice thing about applying Newman-Penrose to KERR-SCHILD spacetimes. It really simplifies things. This is generically, I can always put my metric in this form. V is a real function, and it's related to sort of the total mass of your spacetime. And then phi is a complex function that appears in your tetrad. And the nice thing about this is that phi actually obeys an equation of motion, which is box phi equals 0. And so right away we know that we can use that k hat operator, which now I've written it down explicitly in these light cone coordinates. And that's going to give me a solution to the self-dual vacuum Maxwell equations. So this is the idea of the Newman-Penrose map, is I can always, for these gravitational solutions, I can always find this function phi. And from that, I can get a gauge theory solution, a Maxwell solution. So cool, but is it really going to give me something that makes sense? And the answer turns out to be yes. So once again, I can look at SCHWARZSCHILD as sort of the basic example. And this is what we knew before. And I can write K now in terms of my light cone coordinates. And it's a little uglier, but it's still the same thing. And remember that the function phi is sort of the ratio of my d zeta bar component to my du component. So in this case, phi just minus 2 zeta over 2r plus b minus u, or written in Cartesian kind of coordinates, it looks a little simpler. So, okay, I have my phi. I know what my k hat vector, my k hat differential operator looks like, and I can just form my gauge field. In light cone coordinates, it looks like this. But if I convert to, say, spherical coordinates, it looks really, a lot simpler, and it looks like exactly what we would expect. So we get dt over r, that's just a point charge. Dr over r is just pure gauge. This imaginary part is exactly I times a magnetic monopole solution. And we sort of had to get that because we're talking about self-dual equations in this case. And then this last term, again, is pure gauge. It's just a function of theta times d theta. So we get what we expect, which is nice, from Schwarzschild over to the gauge theory side. And we also get something that matches up with the KERR-SCHILD double copy. Okay, so another example that we can think about is this photon rocket that I mentioned earlier. So this is an example of a non-vacuum and non-stationary solution. So the stress energy tensor in this case is equal to something like k mu k nu, where it's the same k vector. So this is the gravitational solution describing a particle moving along an arbitrary time-like world line. So it has arbitrary acceleration also. And you can write it down or parameterize it at any point in space-time x mu by looking at the backwards light cone of that place and where it intersects this time, the world line of the particle. That vector is sigma, or sorry, the point where it intersects is y. Tau sub r is just the retarded time, and tau is the proper time along the world line. And sigma is sort of that null vector along the light cone connecting those 2 points. So exactly what all these definitions are isn't that important, but we have this written in a KERR-SCHILD way, and k mu is proportional to sigma mu, which is a null vector, so that makes sense. Lambda here is the velocity of the particle, so it's the derivative of y with proper time. And r is just a sort of invariant distance we can make. Also, this is a photon rocket, so it's the acceleration is caused by emitting photons in the backwards direction, so the mass can change. So that's why it's the mass as a function of time. Okay, but anyway, we have a space-time, it's in KERR-SCHILD form, so we can just apply our different double copies and see what we get. So for the first one I want to look at is the KERR-SCHILD double copy. I can just form my gauge field by multiplying phi and k mu together. This is what I get, and this gauge field actually, it describes an accelerating point charge, which makes sense, but it doesn't have the radiation associated that you would really want with an accelerating charge on the gauge theory side. And it doesn't satisfy vacuum equations. It actually has a source for Maxwell's equations, and that source is proportional to the vector k mu. So there's some double copy of the source that happens in this case. And in this paper, when they looked at this solution, they sort of added in the radiation field for this particle by hand in order to get a vacuum solution for Maxwell's equations. And then this gauge field is exactly the Leonard-Weichert potential, which is the potential of an accelerating point charge with radiation. And now it's a vacuum solution. But they did have to sort of massage this a little bit to get what was expected on the gauge theory side. On the other hand, for the Newman-Penrose map, I can write down my vector field sigma in this way, where I've chosen some coordinates for the point where my world line intersects the past light cone. And then I can just read off phi. Remember, it's the ratio of d zeta bar to du. And so my phi is just this, zeta minus zeta naught over V minus V naught. Acting on that with the K hat operator gives me exactly the Leonard-Weichert potential immediately. So in this particular case, it seems like the Newman-Penrose map has a more straightforward interpretation of the double copy. And then one last example, I just want to point out, this is from the newer paper that hasn't come out yet, but we also can look at more complicated spacetimes. In particular, KERR-TAUB-NUT exhibits double Kerr-Schild form when you go to 2-2 signature. So there's phi KK and psi LL. So here phi is something like the Kerr part of it, and psi is, this N is the nut charge, so that's associated with that. And there are two null vectors, K mu and L mu, from which I can extract two different phis, which look like this. X here is sort of the analytic continuation of my zeta coordinate from earlier, since I'm in 2-2 signature now. And I can, once again, do my, I'm going to look at the A equals 0 limit of this because it's simpler to see. But if I act K hat with my electric charge times phi K and my K hat with my nut charge, so that's the magnetic charge times my phi with associated with the nut vector, it gives me exactly what you would sort of expect, which is the QE plus IQM times the self-dual dion kind of a thing. So the real part of this is a dion, and then we also have, since the solution has to be self-dual, it's we also get the imaginary part times the dual of that, plus some pure gauge terms. So everything works out, we get exactly the same thing as the original Kerr-Schild double copy gets to. So just a list of the solutions that I had before. Now looking at them in terms of the Newman-Penrose map, we get Schwarzschild to work out, Kerr works out. Plane waves, we can't apply our formalism because we made that assumption about an expanding congruence. And then KERR-TAUB-NUT, as I showed very quickly, is related once again to the rotating dion. Photon rocket is maybe more straightforwardly related to the potential for an accelerating point charge with radiation. And then also in the newer paper, we're looking at things in ADS or and DS backgrounds. And then for the BTZ black hole, that's in 3 dimensions. So we can't apply our Newman-Penrose formalism in that case. But this formalism generically applies to non-vacuum and non-stationary solutions. So that's something that's a little different than other versions of the double copy. Okay. So just to summarize what the Newman-Penrose map is, we start with some Kerr-Schild spacetime with an expanding shear-free null geodesic congruence. So this is a Kerr-Schild spacetime. There's a function phi that appears in the construction of this preferred null tetrad, and we know that that function satisfies the differential equation. That box phi vanishes. And from there, we can construct a gauge field by acting with this operator K hat. And we know that that's going to satisfy the vacuum self-dual Maxwell equations immediately. Okay, sorry. So there's some things you might look at and question about this. For instance, there's K hat associated with phi, but is there any reason I could choose a different version of K hat or a different normalization of this vector L in my tetrad? What would that change? Is it still going to give me the same thing? Basically, why is this phi associated with this K hat? So for the normalization of the vector L, we want to keep this as a real geodesic. So the only other choice besides setting du to be 1 in this expression would be to set the coefficient of dv to be 1. If we set the coefficient of d zeta or d zeta bar to be 1, it would no longer be a real vector. So there's a choice there with du and dv being set, which one is set to 1. The choice of k hat, there's really only 2 independent ones here also. Basically, this expression switched with u and v is another option. So the question is, why is this k hat associated with this phi? And to answer that, we went to twistor space. So we don't do use a lot of the twistor space formalism. There's a lot of really deep technology, and thank you, Sylvia, for going over some of the background of that. So I don't have to, which is nice. But we can come up with a geometric argument about why this k hat is associated with this phi. That was what we wanted to do. So we start with a null twistor that's coordinatized by these two spinors, omega and pi, like Sylvia was talking about. And we choose a normalization for this. So LAA here is the null vector from before, but now written in this spinor notation. And pi bar A, pi A is the null vector associated with this part of the spinor, or part of the twistor. We choose this normalization so that LAA, pi bar A, pi A prime is 1. And we know that whenever we have a null twistor in twistor space, that's associated with a totally null alpha plane in complexified Minkowski space with a real null geodesic. So the null geodesic here, so that's inside the alpha plane, is this pi bar A pi. So I know I'm not going into all the technology that's in this. If you know it, that's cool. If not, I'm sorry. So the totally null alpha plane, it's in complexified Minkowski, so it makes sense that it's totally null. There's going to be a tangent bivector associated with that alpha plane, and I'm calling that tau. So basically, if I have the normalization of L, where du, the coefficient of du is set to 1, that tells me something about my null twistor, which is going to tell me something about the alpha plane. And the tangent bivector is going to look like this. I'm sorry, I can't show my cursor, but it's the tau is proportional to partial u wedge partial zeta. I can lower an index of that, and that gives me exactly the k hat factor that I've been using. So this is a connection between setting du to be 1, the coefficient of du to be 1, and the k hat vector that we use in our paper. If I instead look at setting the coefficient of dv to be 1 in my null vector, that gives me a different alpha plane and a different tangent bivector to the alpha plane, which is associated with sort of the opposite version of k hat. So this is nice. It gives us a nice sort of geometric interpretation of why a particular k hat goes with a particular phi. And I can do either one. So either the k hat going with this tangent bivector and this phi gives me the exact same equations of motion and the same field strength as the k hat on the right-hand side associated with the phi that goes there. And I can write down these sort of coordinate independent versions of k hat in terms of both my original null geodesic and this null twistor spinor components. And I have my gauge field associated with that. So twistor space is useful for giving us a more basic understanding of where our map comes from. Okay, so now I've gone pretty fast, but just to summarize, the Newman-Penrose map applies to a general class of metrics that include non-vacuum and non-stationary solutions. And it always is going to give you a map to a self-dual gauge theory solution, vacuum Maxwell solution. It has to be in 4 dimensions because we're talking about the Newman-Penrose formalism, and we also don't have sort of the explicit double copy structure that the KERR-SCHILD double copy had. We have a twistor space formulation, which gives us a coordinate independent version or definition for our k hat and our phi, which is nice. So general conclusions. There are several different versions of the classical double copy. I talked about a few of them, the KERR-SCHILD, the self-dual, the Newman-Penrose map, and then Sylvia talked a little about the Weil double copy, and other people will too. And these all sort of agree where they overlap, and it would be really nice to unite these formalisms and understand if they are secretly all the same or what's different about them. And I think twistor space is probably going to be a useful arena in which to investigate all of these different things. Some open questions about the classical double copy in general is how does gauge invariance, that, or at least that I think are interesting, is how gauge invariance on sort of the diffeomorphism invariance on the gravity side relate to gauge invariance on the Maxwell side or the non-abelian theory side. And also most of the classical double copy stuff we looked at is in position space, whereas on the amplitude side, everything is formulated in momentum space. So do these things translate into one another? And the last, but probably most important question is how can we extend this to nonlinear theories? So the amplitude double copy really needs this kinematic algebra structure, right? Which we've just been looking at linear solutions. So we don't have that. So going to nonlinear on both sides is going to be really interesting. Okay, that's all I have. Thank you.
Thank you very much for a very interesting talk. Right. Do you have any questions from the audience?
Hi, very nice talk. I just wanted to ask, you were saying at some point how there was a difference between the Newman-Penrose map and the standard KERR-SCHILD formulation, and it was the radiative part when you're talking about the Linear-Vickert solutions. And I was just curious, is this a general feature or was that for those specific solutions? Do you know?
So this, I think, this is the only specific situation I know where this happens, and it's because they are looking at a non-vacuum solution, I think, and the KERR-SCHILD double copy is only really sort of guaranteed to give you a solution in the case of a vacuum spacetime. But this particular spacetime is not vacuum.
I see. So it's not. So, and do you understand why in your formulation you didn't have to add the radiative part by hand, or?
So in our formulation, sorry.
Yeah. So something seems to make it just appear there.
So the reason we had to get, like, no matter what we got, we had to get like a vacuum solution. I don't know, I mean, the deeper reason, but we're going to get the vacuum solution, and the Linear-Vickert potential is a vacuum solution of Maxwell's equation. So
I see. So automatically it had both parts because of that.
Right. And in this case, they have when they don't have the radiation field separately, right, on the gauge theory side, they have a non-vacuum solution for Maxwell's equation.
I see. Thanks.
Yeah.
Any other questions from the audience?
I think Ricardo.
Oh, sorry. Yes, please, Ricardo.
Yeah. Hi. Thank you. So you get always a self-dual field from any metric, even if it's a real metric.
Yeah. So self-dual once I map it back to Lorentzian spacetime. Yes. If that makes sense.
So let's say when you look at Schwarzschild, the solution you get is what is somehow Schwarzschild plus I pure net.
Sorry, it's not self-dual on the gravity side. It's only self-dual on the gauge side.
So sorry, exactly. So you get like Coulomb plus I magnetic monopole.
Right.
And also in this radiation story, well, I guess what we were arguing there is that the current represents secretly the radiation, and then the surprise thing is that in gravity, that you know, it's less trivial that can be the case, but it was indeed the case also. But so this linear visual potential that you mentioned, is it then also a complex field? And should we think about the real radiation field as its real part, or?
Right, yeah. So this is, sorry, I went over this quickly, but yeah, this is after I've taken the real part.
Okay. So after that, second inequality is the real part.
Yes, yes.
Mm-hmm. I see.
And there's also a pure gauge part too that I didn't write down. So, but yes, yeah, this is.
Okay, thank you.
And Sakib Hassan.
Hi, thank you. I just had a question about the conditions on this construction are that you want shear free and expanding the congruences. And I'm just wondering why things like vorticity, for instance, are like, does it not matter? Like, because I can imagine you can have solutions that are of the Einstein equation that are like Bianchi type solutions that have non-vanishing vorticity, but also like null congruences with non-vanishing vorticity. And like, is there a construction for those as well, or does existing vorticity ruin something here?
That's a good question. I don't really know. I know, so maybe, I'm not sure if there's a metric that can be written in Kerr-SCHILD form with vorticity. Do you know that? I don't know.
I'm not sure actually. I'll have to see. But Bianchi type solutions often. Okay, I'll have to see. I'm not sure. But
Yeah,
in any case, what is it? Is it the case that if you have Newman-Penrose type thing, vorticity is exactly zero? Or sorry, you have this Kerr-SCHILD type thing, where the vorticity is automatically zero?
I'm
I
not sure
imagine
if that's
right.
true. Yeah, I don't. Yeah, I'm not sure. I guess I would have to look that up. But I know that when you look at just Kerr-SCHILD spacetimes with these assumptions, I know this restricts to Petrov type D and 2 only. So those are the only ones that can we can apply the formalism to. So
Okay,
I don't know
thank
if
you.
vorticity applies in there. Yeah, sorry.
It's fine. Thank you so much.
Any other questions from the audience? Yeah, actually, could I ask a naive question? So one of the things you mentioned was that your construction is your construction is restricted to 4 dimensions. Does Newman-Penrose extend at all to higher even number of dimensions, or is it exactly 4?
So I think there is a construction for at least 5 dimensions, I thought. I think there are constructions, but it's not nearly as well understood or well studied. And yeah, I agree, we should look at that. We just haven't. But yeah, I think there are higher dimensional constructions for the Newman-Penrose formalism. It's just not as well understood.
I see. I mean, I mentioned even because you wanted to find null tetrad type things, and so if you want to pair them up in a complexified way, I mean, so that's the obstruction you run into in 3D if you try to do it. Is that right?
Right. Yeah. So yeah, I'm pretty sure people have done it in 5D, but I would have to look that up. But yeah, I think it should. I mean, it makes sense that it would be straightforward to extend to even dimensions. I agree with that. Yeah.
And one of the novelties in your construction is that that does not have to be on vacuum anymore. So
right. Yeah. Or stationary. Right.
In that case, does the stress energy tensor does it factor into tensor source for the Maxwell equations?
On the gauge theory side, the stress energy tensor. So then in that case, it's always going to be a vacuum solution on the gauge theory side. It's non-vacuum on the gravity side.
So it's okay.
Yeah.
And is that expected? Well,
I mean, I don't know, right? Like, I guess we don't know exactly what should map to what, right? But at least it's sort of whatever the mass distribution is on the gravity side maps to a similar sort of charge distribution on the gauge side. So it seems to make sense.
The charge distribution, well, okay. I mean, does the charge distribution count as a delta function type source?
Yeah, sorry. Yeah. So when I mean vacuum, I mean delta function. Yes, I'm being vague about that. You're right.
One of the last things you mentioned in your last slides was gauge symmetry. So is the whole formalism manifesting invariant into gauge transformations, like coordinate changes in the Newman-Penrose side, or
so we have this twistor space formulation that is sort of coordinate invariant, right, for the Newman-Penrose map, and then once we get the gauge solution, we get rid of things that are pure gauge in the gauge theory sense, but we don't have a map, I guess, between the gauge symmetries on one side to the other. Does that answer your question?
I see.